it was kind of awkward how we ended test 2 bracket with one of the tougher things that we do, which is reaction yields. And remember, we do that by, you want the delta G of a reaction, and this is the real delta G, not just the delta G from these are per mole, per mole. Remember, these are actually chemical potentials, which chemical potentials define everything. You just saw me screw up. I almost didn't write the per mole. That actually is terribly important, but what I always do is I just think of this as per 1 mole, so it doesn't actually change anything. This is what you really need to know. This is what you learned in high school. Again, the Hess's law bit. And then you've got this thing. Now, again, you did also learn about this in freshman, but your version of the reaction quotient was not correct. Regardless, okay, so if you want to know what product distribution is at equilibrium, well, there's no more driving force. Simplifying this substantially, obviously get minus. So you get the Hess's law result, the high school thing, and now that's natural log of K. And then you have to decompose K into mole fractions, partial pressures or mole fractions. So we're doing gases still, and I'm going to have you do a gas phase reaction in your homework. So we got one more homework with this stuff, and I'll put it on test 3. I left it off test 2 because I felt like you were already being overwhelmed with what we had covered up until this point, and so I left it off because this is probably this is like everything we've been doing was just to get to this, because what else could you ever want to know about thermochemistry other than how much does the reaction go? I mean, that's why are you handling chemicals to begin with, right? So now, as an example I have in what you're going to do in your homework is this one. And it's I'm doing a couple of different things than I did with the water one. And what I'll do on like test 3, I'll have just like a hypothetical A goes to B or something like that. These are all gases. Another thing I tend to forget is to put that there's some kind of equilibrium. You don't need to write this down. We've already covered this. I just want to point out that K can be decomposed into mole fractions. And remember, the stoichiometric coefficients sit on top, and that comes about from entropy being a natural log. If you recall all that derivation, I'm not going to cover all that because it takes a really long time. Okay, and 2. Okay, so remember that there is a component due to mole fractions, and then there's a component due to pressure. All right, big picture. Let me step back. Remember where this comes from. This comes from changing the chemical potential, or the G per mole, of chemicals as they mix, but as chemicals react, their mixing changes. So this is entirely an entropic result, right? And I know that because there's a natural log. Every time I see a natural log, even if I see a natural log in like descriptions of planetary motion, it's entropy. Maybe they don't even know that, but it is. Okay, so this tells you how Gibbs energy changes when things are mixed, because this guy was tabulated for pure substances, but when you mix things, their G's change, and this takes into account as they are mixed, before they react, and as they react. As they react and stop, that turns to 0, leaving me a simple way to get to the answer, which is all right here. And so again, because of this natural log, the stoichiometric coefficients in the derivation, look it up, sits on top. We did cover this. And because these are gas phase reactions, the mixing I put into the form of partial pressure, and then I express the partial pressure as mole fractions. I'm sorry, I'm explaining in words something that was like remember that 2-hour derivation? So I'm just doing that over again in words. So that's where the mole fractions come from. That's the part you solve. We've got the STP initial pressure, which we'll just say is 1 bar. And I have to, because this number here was tabulated at 1 bar, I have to use that. And then this would be the actual pressure. Now, what I'm going to have you do on your homework is first do what you would do on a standardized test, which would be to say, so the standardized test sometimes, they don't want you to be overwhelmed and I mostly don't want to overwhelm you. And they say, do this reaction assuming that you're at 1 bar pressure. So notice that you just ignore all this, right? And that's all fine. It's just that that's incredibly unrealistic. This reaction naturally bleeds pressure, right? Because it forms less gas. So what I'm going to have you do is figure out the mole fractions, and you're going to use that extent of reaction alpha. I set it up for you on the homework in case you forgot how to do it. I express all this in terms of that alphabet. Alpha is at 0 means it doesn't react. Alpha 1 means it fully reacts. You figure out what it is from the data. And so I've given that to you. And part A, you just assume all this is 1. Part B, you're actually going to let that change. And remember, this is the Le Chatelier's principle. And you're going to see how K doesn't change with pressure. You're going to see how this shifts in response. And that's a mathematical proof of Le Chatelier's principle. So that's why I think it's kind of neat why I'm throwing that at you, to make you do that so that you can mathematically prove Le Chatelier's principle, which applies to a lot of, I see Le Chatelier's principle even in economics. I'm taking an economics class. So I actually see conservation of energy. They call it conservation of money in economics. Debits and credits, they have to match. That's actually conservation of money. So what you do, though, to solve this is that you need to come up with a phenomenological model for pressure as in terms of the reaction quotient. So here, I'm just going to go ahead and help you out with that because it is a bit of a tough question, and then we're going to do electrochemistry, which is easy. What you need to do is model the pressure as a function of the extent of reaction, this alpha bit. And let's say that you start at 1 bar. That's if alpha is 0, and then pressure has to be, let's see, a half a bar if alpha is equal to 1, right? So what you have to do is figure out a phenomenological model that will simulate this. And so I can figure that out pretty quick. That's 1 minus 1/2 alpha times a bar, and that doesn't matter because units will cancel. And that's the number 1. Is that right? 1 to 1/2, right, there you go. Okay, so you got all your alphas in here, and you then figure out how to get it equal to that. You're done. Then, and you do all this on Mathematica, then you're going to have an extra little term here. You're going to have this squared. You ask Mathematica to solve it, and you'll find that alpha has changed in the result. Now, what you find, of course, is that you're going to actually not form as many products because the Chatelier's principle will resist the drop of pressure. That's what you're going to find. So, anyway, again, that's not the kind of question. I'm going a little too far with this, but to my credit, you'll do it all on a computer, and I just think it's really cool that you can prove Le Chatelier's principle. I think that's fascinating. Last bit on this stuff. Actually, I wasn't going to cover this, but when I was looking at your tests and I see what you're strong and weak on, I've just talked about how pressure changes in Le Chatelier's principle, but K will change with temperature. K is going to change with temperature. If anything, because there's a T right there, if that confuses you, at the bare minimum, I can just point to a T right there and say, you see how that's T on the left and K is on the right? Therefore, K will change with temperature. So that makes a lot of sense to me. Even if that doesn't make sense here, let's prove it. Let's work with ln(k). I'm just going to assume we're at equilibrium. And here's the Hess's law deal, which is just a number you look up. And we've got this. Now, I want to see how K changes with temperature. And again, normally I actually have been dropping this, but I think you need a little bit of a boost in terms of your mathematical prowess from what I saw in question 12. And what I want to point out that if this, again, why are you handling chemicals if you're not doing a chemical reaction and you want the reaction to work? Now, since K is ratios of products over reactants, ratios of partial pressures, ratios of mole fractions, and as we get to liquids, actual biochemistry, they're activities, by the way. Notice that activities don't have units, and neither do the units of K. K has no units. Anyway, we're getting there. So I am going to introduce activities and how to do reactions in solution. and I forgot what I'm talking about. Actually, I totally forgot. Anyway, okay, so activities over products over reactants. Obviously, we want K to go up. So I want to know, I can quantify how much K goes up, but I really just want it to go up in general. Now, as I stated before, messing with pressure is kind of a bad idea. For one, it's impractical, and that's one of the reasons I want you to do the Le Chatelier question. It's impractical. It's really difficult to do a gas-phase reaction in an accordion type of vessel. Why would you build that? It's going to be really expensive to build a big machine that looks like an accordion. Why would you do that? So when it comes to temperature, what you're going to do is heat things up. So you want to know, that's really your only practical option, and let's think in terms of like, I'm making 100 million tons of ammonia a year. Okay, so temperature is your real tool. Not so much pressure, but temperature. Okay, so, again, just to know whether this goes up, I don't really actually need to solve for K. And that looks like a bear, because what I have is K is equal to E to all this jazz, and then guess what? I'm going to take a derivative. All right, instead, natural logs are really fairly linear. It's not like it goes up and down and back up again, because that would be confusing. Natural logs keep rising just like a line keeps rising. So if I want to know whether K goes up or not, I can look at whether K goes up or not, or I can look at whether ln K goes up or not, because those are the same thing. Because again, natural logs are rather linear. For something that's not a line, it's as close as you can get. Okay, my point here being is I can do this. I can just take the derivative of ln K. Again, if it goes up or down, this is going to tell me just as easily as K itself, with the benefit of being obscenely easier, right? And so, how much obscenely easier? I'm going to drop out a 1 minus R. And don't try to, one thing I noticed that a lot of you folks are just trying to memorize stuff, and I keep telling you not to. So don't worry about, if you're studying and you look at this, I have to memorize the 1 over R comes out. No, you don't. I'm just doing it for convenience. If I didn't do this, I would still get the same answer. I'm able to do this for one, it's convenient. Number two, R is a constant. But you don't try and memorize that kind of stuff, okay? So then, I then do the derivative of delta G over T with respect to T. Look familiar? Yeah, Gibbs-Helmholtz, right. I told you it's going to come back a zillion different ways. We're actually going to do this in unbelievable. We're going to spend like all day doing Gibbs-Helmholtz equations when we do colligative properties. And I should know that's minus 1 over R. And the Gibbs-Helmholtz deal is minus delta H. And I got to remember that this is delta H in the table in the back of the books over T squared, which is delta H over T, RT squared. Okay, so you just lose the minus, by the way. That's really as complicated as it gets. Okay, now as usual, I bring this thing over to the other side and integrate it. And okay, so I'm integrating lnk, integrating the change in lnk. There we go. And this is here. I'm not scooping over, you can see. I'm going to integrate this right here. And I'm not going to ask you about whether you should hold H constant or not with temperature. You should not, obviously. And of course I need units. I'll do T1. Of course that'll be 298. Okay, and T2 will probably be a higher number because again, heating things is easy, refrigerating them is not. Now remember that this is, because I am kind of concerned about how you folks you're struggling a little bit more than most with applying calculus to things that are not X, Y, and Z. So what I would point out that the lower limit would be what? K1? What would the lower limit be? Remember, you have to match them. It's what? Yes, it's ln K1. We'll just call it our initial one, I or 1 K1. ln K1, which again, you've already figured that out. I've given it to you or you've just calculated it, and the upper limit is what you're looking for. Now, remember the principle here, if I ask that, what I'm really testing you on is when I was your age, if I saw the change, change in X, change in Y, I have no issue with. I've been dealing with that since sophomore year of high school. But change in LNK, what the heck is that? It's really not an issue at all, as long as you just change your limits, right? Then there's really nothing to do about it. All right, so what do you do with this? Okay, I'm just going to go ahead and integrate it. And of course, I am going to ignore the fact that delta H changes with temperature. I'm just going to ignore that because this is complicated enough already. Again, you've been given this information. And you look this one up in the table in the back of the book. And of course, what I'm really wanting to figure out is, does it go up or does it go down? And I want to think practically. So this up here, 2.1 or 298. Again, I'm just being practical. T1 is always going to be 298. Okay. All right, now, remembering that natural logs are basically just like lines. I just can, in my mind, I've just not even seen the natural logs because I really don't need to. What I am observing here is that you run into relationships like this a ton. Even in my own graduate, like research, level stuff, PhD stuff, I run into this a lot, and it always gives me a headache. But I just remember, I've seen it so many times, I've got it drilled into my head. You don't, nor should you, so you use a calculator to prove that T2, of course, will be higher than 298. 1 over a big number minus 1 over a smaller number is what, positive or negative? You see, you're kind of confused, aren't you? Calculator, 1 over a big number is a small number minus a big number is negative. Okay, again, use a calculator. All right, so negative. All right, so if you want this to go up, you need to negate that negative, which means delta H has to be positive. Right, negative. You already got a negative, fortunately. Delta H means to be positive. Okay, so positive delta H is endothermic or exothermic? Okay, right, endo. So, in endo. And so if that's the case, you have A goes to B. And let's see, I'm actually kind of forgetting. If it's using up heat, if it's using up heat, and heat is a reagent. So, because there's no heat on the other side, that's why it's cold, that's why it's endothermic, right? Okay, so what I get from this is to get more products on a positive endothermic reaction than I would want to add heat. I want to heat it up. I want to add heat because, of course, that makes T2 higher, and that means you heat an endothermic reaction, which I already know is true back when we first studied the Helmholtz reaction. Okay, so it all makes sense. Okay, anyway, so I'm kind of blabbling there. I don't see myself doing much with this on a test because we're going to do a lot more stuff with this Helmholtz. And I'm actually only covering it because I just do want to push you a little bit harder on this calculus of things that are not X, Y, and Z. Because that's the one thing I thought you struggled with a little bit on the exam. And so anyway, let's just drop all this and go to something different. So I'll have this to be a minimal part of exam 3. Again, note, exam 3 will begin with perhaps a very simple calculation of a reaction quotient of a K with an alpha, and of course I'll keep it simple. A goes to B, and that will be very easy. The one that you're doing on the present homework will be a bit harder. And that's only 2 questions, I think. And then you get to, I think, something that's relatively easy, and I used to never cover this. Electrochem. All right, so this will be relatively easy, and I will definitely have maybe 2 questions on the next exam on electrochem. We're only going to spend today, and I think just a little bit today and tomorrow on it, and that's about it. And by the way, what we're going to do from now on, this part of the class is really funky, because as of right now, I'm done with all these delta G's and H's for the most part. They're going to come back and forth sporadically. But this third of the class, if it was up to me, I would not cover the material that I'm going to cover. But your standardized exams will have the material that I plan to cover, so I will cover it. Otherwise, I'd be screwing you over. But what are we covering? We're going to cover just a bunch of hodgepodge of stuff. What factors govern solubility of liquids in other liquids? What factors, how do you know if adding a salt to water makes it hot or cold? What governs the solubility of a salt? Oh god, electrochem. All right, so we're covering just a bunch of random things. And I think they're personally really dated, but they're on your standardized tests, and I will not leave you hanging in that way. Personally, I would actually cover more intricate stuff, graduate level even, but I don't get to decide. So just understand that every week we're going to basically cover something kind of different, and they are relatively unrelated. That makes test 3 a little bit harder, because test 1 and 2, that's one reason I cut it off actually at the reaction quotient, is it's all kind of flowed together. It's been comprehensive. All right, that's a little bit bad, but it's also thematic, which is good. You're always studying the same thing, just to a higher and higher level, and that's good. It makes it easier. Now it's just a bunch of stuff, and I'm sorry about that. But one reason, so I used to not cover electrochem, but one reason I am is because the world's about to end. So we are going to run out of oil. There's something called Hubbard's Peak. Any of you heard of Hubbard's Peak? None of you? Hubbard's Peak is the day that the last new oil well is dug. And because there's only so much oil in the ground. And actually, oil company executives keep saying that the earth is actually generating oil all the time. They have actually there's every piece of evidence say that that's not happening. They just don't want people to behave and legislate with the idea that oil will run out, which it will. By the way, of course there are ideas that the earth is hot and under pressure. And you know where the heat of the earth comes from? And it's tempting to say it's gravity, right? Just crushing the interior so that it's hot. You know, when you crush things, they seem to get hot. Is that true? That would be generating energy from nowhere, by the way. If you use gravity, I mean, yes, I can use gravity to turn a turbine in a hydroelectric dam, but what about when the water's already fallen, or the ground beneath me, right? It's already there, it's not going anywhere. How could that be used to heat up the interior when it's not really moving, right? There's no work. So do any of you know where the temperature inside of the earth comes from? None of you know? I mean, sort of God, you know the earth is hot, right? Underneath this, lava. You don't know where the energy from lava comes from?
Burning oil.
Burning oil. George Bush. Radioactive decay. Radioactive decay. Radioactive phosphorus, specifically. It's one of the bigger ones. Yeah, that's where it comes from. Where actually the universe is largely shedding new heavy elements, right? The universe created a certain number of heavy elements, and they're just continuously decaying ever since then. New ones are made in stars up to carbon, but then that's about it. So anyway, so we are running out of oil, and Hubbard's Peak is the day that the last oil well gets dug. And ever since then, now that's not the last day of oil, that's the last day of a new oil well. And ever since then, which will be around 2040 to 2050, since then, we will only use up the oil in existing oil wells, which will very quickly run out. Now, one thing that you've got to be careful of is that when you see the news is full of lies because they don't want to scare you, they want to control you and tell you how to vote, entertain you so that you'll watch their advertisements. When you see a new, we discovered oil here, or we're getting oil from oil shales now, and there's so much oil, wow, it's going to last a long while. And you think, oh, is it good or bad? We got new oil well, we found oil shales. We're going to get oil from oil shales in Canada. Is that good or bad? It's very bad. Not so much, environment, yes, okay. Fracking, yes, bad for the environment. But it's much deeper than that. Let's say global warming wasn't happening, like some people believe. The reason it's very bad is it shows desperation. That's what is more scary. This has nothing to do with, oh yeah, I guess there's still plenty of oil. Actually, that's the exact opposite is true. There is less oil. And because there's less oil, going towards harder sources of oil becomes profitable. Normally they wouldn't touch this stuff. It's too hard to get out. But oil is becoming so rare, it's becoming so expensive that now it's worth it. But the problem is once they're done with the oil shales, there's really nothing left. That's why you should be terrified when you see that good news. It's actually terrible news. So our ideas about improving the future are to, not burn oil, and solar seems to be the way to go. There really is just no other option. Nuclear is a possibility, but the problem is that we don't build powerful nuclear plants, right? We don't. Because nuclear is too scary. In fact, the United States just put its first nuclear reactor online in 20 years in the TVA. I forgot where, some southern state. But first nuclear reactor in 20 years, and it powers, I think it was 1 million homes, or 10 million homes. That's next to nothing. There's 330 million people in this country. That's next to nothing. I think it was just 1 million, come to think of it. It's next to nothing. We could do better. It's just that if anything goes wrong, kabammo. Well, I guess you don't have to worry about powering those 10 million homes anymore because the people are wiped out. So we do not build powerful nuclear power plants for that reason, and we shouldn't. But the problem is that limits nuclear's effectiveness. So the other idea is solar. Now the problem is solar doesn't stay on all the time. So guess what? How do we store the solar energy? Batteries, yeah. Now there's other ways of doing this. This is actually really cool. This actually would be surprisingly effective. You would actually use sunlight to power air pumps that will pressurize caves. I swear to freaking God, it sounds like it's from a science fiction book. You pressurize air in a cave, and when night comes on, did I say night comes on? Anyway, when it turns dark, you actually use that high pressure to turn generators. That's actually a very viable technology that's being worked on. Okay, but solar powering batteries, because when you go home around 6 p.m., there's a giant spike in electricity usage because you're turning on your ovens, your electrical ovens. And so anyway, that's why I want to cover batteries. Also, because of electrical vehicles, the Volt, Tesla, which I would like to own if only somebody would lower the price. If I ever buy a car, I'll buy a Tesla. I'm not advertising for them, I guess I am. But they're just kind of cool. I really would like to have one. And this is what we're all going to drive. Now, here's one thing that you might ask yourself is, see, when I was your age, the first electrical cars were being built, and I thought, well, wait a minute. Okay, it doesn't burn gas, but the power plant burns coal. Some they are actual gas burners. It's a little crazy. They do it in Saudi Arabia, if I'm not mistaken. They actually burn oil to make electricity, which is kind of a bad idea. But anyway, they have lots of it, so it's not a big deal. What does it matter if you burn it here or there? What does it matter? Does it? It does actually, because it's actually more efficient. So you will actually get less pollution, but ultimately it does come from burning. So yes and no. But yes, the efficiency is great enough that it's a good idea. So you are all going to be driving electrical cars probably about 10 more years would be my guess. You're not going to have a choice. But one of the things about electrical cars, I remember the Dreamliner. The Dreamliner had big lithium air batteries, not lithium air, they haven't made those yet, lithium ion batteries, right? But who knows what the problem was? They had an initial problem that they had to ground them all. Any of you remember? It's only 2 years. They what? Exploded. They didn't explode, right? They were caught on fire. A couple of them caught on fire, they had to ground the fleet till they fixed it. Why? I'm about to show you why that happened. So anyway, just motivation for why you want to study electrochemistry. Normally, I know this is a biochemistry class, but seriously, batteries are going to be our lives because that's how we're just going to do it. So I really think you should know this question.
How long do you think it's going to take until oil runs out?
Well, all right, so Hubbard's peak is around 2050. And it's a little complicated because what's going to happen is oil prices are going to skyrocket to an unbelievable extent at that point because people are going to realize it's not going to last. Now, here's a crazy thing. I talked about nuclear, I talked about solar. I noticed I was missing coal. All right, we have tons of coal. It came from the Carboniferous eon or era in Earth's history. The oxygen in the atmosphere, instead of being 25%, was 30%, something like that, maybe a little higher. And so forests and vegetation grew like mad. Also, bacteria hadn't evolved to the point they have now. They couldn't break down wood like they do now. So all that carbon in the form of wood fell to the ground, was compressed and heated to the form of coal. We have unbelievable high levels of coal, especially in this country, China as well. unbelievable amounts of coal. Even with population explosion, we can survive roughly 2,000 years, even living the way we're living, which is bad, by burning coal. So why worry, right? Pollution, right. Clean coal technology is important because coal just really pollutes the heck out of our atmosphere. In fact, if we burn coal like we need to, given the population rise, and I hate to say it, folks, it's really China and India, because of their population explosion and use of energy, and unfortunately they're doing it with coal. If we let that happen, in the United States, our infrastructure is already built. We actually have a decent infrastructure. We built it a long time ago. Our population is roughly going to double. But in other parts of the world that have tremendously high population, that are very energy hungry, when they start burning coal, it is going to wreck the environment. So it's not so much us you have to worry about, but so what we need to do is give the emerging countries and their energy usage needs to not be coal. Oh God, that would be so bad. So what would happen is, if we burn coal like we burn gas now, all the other forms of energy we get, the skies will turn black. And we can't live like that. We literally will not live with that. So we don't have a choice. We cannot burn coal the way that we burn coal now, especially because of the volumes we're going to be doing it. All right, so we're going to use clean coal energy, right? Okay, that's a good idea. Guess what? It's expensive. So while we do have thousands of years of coal left, the problem is that it will be so expensive that basically our power will be on, and this is probably how this is going to work out, by the way, folks. In the US, because of our decent infrastructure, you're going to have, the power is going to be on, kind of like in the Philippines, it's going to be on just an hour or two a day. Enough for you to cook and clean, and that's it. You're not going to be able, because you can't afford it otherwise. And that's really what's going to happen. Because, in all honesty, we haven't acted on this. We didn't act on this soon enough. We're pretty much screwed. That's why I don't have kids. So, so, does that answer your question in the most horrific manner possible? Yes, sorry about that.
Can we find another solution though?
So the solution is solar, but the problem is that, so solar and nuclear, because nuclear power plants are small, the reason I didn't talk about this more, my advisor at MIT figured this out. We need to build a nuclear power plant every day for like the next 40 years, starting 20 years ago. It's too late. It's already too late. We cannot solve the energy crisis that is coming because of Hubbard's peak. We cannot solve it because we would have had to have done so 20 years ago by building a power plant every day. Not alone once every 20 years like we're doing right now. That's already off the table. Besides, it is legitimately too dangerous. Solar cells, I don't know personally. What I've seen is that solar cells are made with giant chemical vapor deposition apparatuses on silicon. The problem is with the solar cell, if it develops a crack, it's dead. And we need a solar cell the size of Arizona. A single crack, the damn thing, not a single crack, anyway, you get my point. The damn thing is too prone to damage. And the slightest bit of damage, it's an electrical circuit. One short circuit, the whole device is shot. And so that's the major problem. So we need to make solar cells really, really cheap. And part of it breaks, you can pull that out and put another one in. That's the idea. I don't know that it's technically feasible. The laws of nature, kind of like building warp drives and Star Trek stuff, nature will not allow anything to travel faster than the speed of light. I'm afraid nature will simply not allow us to collect energy from the sun efficiently in a way that we can reasonably afford, such that we won't just end up burning coal. We're going to end up burning coal. But don't worry, we won't do it too much because that will pollute the atmosphere, so you only have power 1 or 2 hours a day, and that's how you're going to live. The good news is, though, is that this is very similar. The reason I brought up the Philippines is that policy wonks that study this stuff say, United States people, you will be living in the Philippines right now. In the future, you will be living in the Philippines right now. The good thing is, your average people, the people in the Philippines are happier than you. Not hard to imagine, right? On average, they are happier than you. So you can look forward to that. Actually, your children, you'll all be dead. Especially on the next day. Anyway, all right, so, okay, I know, I'm rambling. I do have 5 minutes, so let me introduce you to electrochem. And what we want to do is a phenomenological model. Don't worry, I brought 2 backup pens. So yeah, sorry I went off on that, but it's just, it really does bother me because, these problems are real and they are largely just being ignored. And hopefully your generation will not do that. Okay, when it comes to analyzing batteries, we're going to have chemical reactions that produce a current, and that current needs to create energy, and that energy needs to drive your car down the street, right? So that's a very real thing. I can measure how much energy it takes to get you down the street. And that energy needs to come from a chemical reaction. I know how much energy is in a chemical reaction. I know how much energy it takes you to go down the street. Now I can calculate how big the battery needs to be to do that, because I need to do that if I'm going to build a car out of this. So as usual, we're going to go with delta G. Now I didn't mention this before, but I talked about how change in U and H are all heat at constant volume. At constant temperature, A is work. Actually, G is work, just not PV work. So remember that A, delta A, not area like on the test, A, Helmholtz energy is the maximum amount of pressure volume work that you can get out of a system at constant temperature. G is max non-PV work out of the system. Given that I'm going to power a, like a little slot car, except human size, with electricity, that would be an example of non-PV work. So that's why I'm going to use delta G for everything. Besides, constant temperature, constant pressure, right? So, multiple reasons. All right, but what we need to do is get energy out of an electron. Okay, we've got to get energy out of an electron. And what I'm going to do now is derive phenomenologically. I'm just going to write an equation that makes sense. An equation to relate electrons to energy, which is the Nernst Equation. Okay, so what I need to do this, number one, I need to get number of electrons. So I have a reaction. Obviously, this is a chemistry class. Everything's a chemical reaction. All right, that chemical reaction is going to produce electrons, and that will be characterized by a stoichiometric coefficient. What I'm going to do is relate that to charge. And when I was prepping for class, I was almost going to write, in little parentheses, I was going to put M, like moles. That would be wrong. Charge is in coulombs. That's the SI unit of charge, coulombs. N is moles, which is units of moles. So that would be wrong. I'll show you how to get charge from the number of electrons. And then what you want to do is relate that, which is step one, relate that to delta G of the reaction. So that's the goal. All right.
Minus sign for the delta G, first row.
Or is it dash?
No, it's a little dash. Sorry, yeah, little bullet points. I know I'm kind of bad about that, right? Bullet points. They're actually I could delete that. There is a minus sign in the equation. Okay, so let's do 1 and 2. Let's do 1 and 2. What I would do is get the stoichiometric. We're going to have a reaction. I'm going to write the reactions here next time. And they produce, in the reaction, there's a stoichiometric number of moles. And I want to turn that moles into not, remember like I said before, I was screwing up when I was preparing my notes when I was thinking about relating this to moles. I've really done that here. What I need is charge in coulombs. And to do that, I would multiply that by F. Solves everything. It's a letter that solves it. No, it's F is Faraday's constant. And here, I'll write that over here. Faraday constant. And I'll write it down in the next time, actually. It's like 1.9 to the 10 to the 4. Anyway, I'll write it down next time. It doesn't matter. Anyway, all this does is it says, if this reaction produces 2 moles, now I know how much charge is available. And let's see what I want to say about that. Okay, so now I've got charge. Now I'm leaving a blank, and what I need to do is relate that to delta G. Okay. Now, again, coulombs, joules. So I'm going to need to multiply. What's missing in here is something that turns coulombs into joules. Any idea what that is? Well, yes, it has units of joules per coulomb, that's right. But now, okay, half of you were born outside the U.S. If you go outside the U.S. and you have your eye and you have your laptop, what do you have problems with? Plugging it in because the voltage, right. Okay, voltage, which has units of joules per coulomb, is how you convert coulombs to energy. And the reason that is because, this is a little bit of an aside. Why? Why? Because electrons have no internal structure. Okay, electrons have no internal structure. They don't vibrate, they don't rotate, they only move. And that means that I can only get energy from electrons by messing with their kinetic energy. Now, the way I mess with their kinetic energy, being a little bit of an old-timey physical chemist, I know how they actually make the cathode ray tubes inside of old television sets, which were old television sets in my perspective only very recently. What they do is have a charged plate. Let's say it's at 1 volt, right? 1 volt. What you do is, and this would have been the screen, by the way, on your old-timey television set. What you have is an electron gun, which is a fancy way of saying a light bulb that gets hot, literally a tungsten filament, and electrons are flowing through it. It's kind of shedding electrons, and what happens is an electron will wander through the hole and then bam. They just want, literally, they're just kind of floating around, but if they happen to float through a hole, they see a potential, sorry, this looks awful. They see a potential difference. They see that positive plate and they fly towards it. And the amount of energy they gain is, by the way, called 1 electron volt. So you see how I can get energy from electrons by making them fly through a potential difference. This totally makes sense. I just want to point out that this is energy, right? The electron has gained kinetic energy. It only gains kinetic energy by going through a voltage. And you know that. And again, a demonstration of how old television sets work. And actually, I don't know if I want to say anything more about that. Anyway, I'm going to leave it there. But the last thing I want to point out is that this is called the Nernst Equation, but because people used to think that electrons were positively charged, there's a minus sign. Anyway, next time I'm going to go over more about the Nernst Equation.